Good morning. Welcome to Playing Offense and Defense with Deepfakes in Lagoon JKL with Mike Price and Matt Price. Before we begin, a few brief notes. Please stop by the business hall located in the Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2. There will be mimosas at 11:50 and an ice cream social at 3:20. The Black Hat Arsenal is in the business hall on level 2, and lunch will be available in Bayside AB from 1 to 2:30. Don't forget the merchandise store on level 2 and session recordings from Source of Knowledge. They have a desk on every level. Questions after this talk will be taken in the wrap room, Reef A, which is just down the hall. And please remember to put your phone on vibrate or turn it off in order to avoid interrupting the presentation. And now, please welcome Mike Price and Matt Price.
Hey everybody, how's it going? My name is Mike, and this is my colleague Matt. We will be giving a talk to you today about playing offense and defense with deepfakes. But to get the big question out of the way up front, no, we're not brothers. So we do have the same last name, and we have the same first initial. So we have awesome names, but we're not brothers. So with that out of the way, I'll jump right into it. The way that we've structured our presentation today is to talk in the first half about details related to the offensive use of deepfakes. So it's kind of exploring that topic. The first thing that I'll talk about is to try and pin down a basic definition of what a deepfake is. So it seems that different people have different opinions of kind of what the term deepfake means. I'll give you my version of what I think it means. Then we'll talk a bit about why we think deepfakes may become a problem. I have on the slide here are a problem, but I think it's a little bit more of a potential future issue. I'll go over some of the public examples that are relevant to the topic of offensive deepfakes. So not wild examples because there aren't many of those, but just things that are relevant to that topic. Then I'll spend a little bit of time talking about some investigating that I did into how deepfakes are created, and then I'll go through a few quote unquote offensive videos that incorporate deepfakes as the final part of my portion of the presentation. Then I'll turn things over to Matt, who will talk about the solution space, including work that other folks have done to try and solve the deepfake problem, so to speak, to build detection capabilities. And then Matt will delve into a detection methodology that he's developed himself. And then we'll wrap things up at the end with a brief note on DeepStar, which is a tool that we created in conjunction with this presentation and that we plan to release in the next couple of days. So with regards to what a deepfake is, I thought it would be cool to talk briefly about the history of deepfakes. So it's a relatively new technology. They have really, I would say, only been around in practice for the last couple of years. The first research that I'm aware of personally that came out related to this topic came out in 2016 via the Face-to-Face project. This is a cool project. If you search on YouTube, you'll find example videos from it where some researchers were able to control the facial expressions of a well-known person, George W. Bush, by placing themselves in front of a camera and essentially controlling George W. Bush in real time, including all the movement of his face. If you fast forward a little bit to the end of 2017, the deepfake subreddit was created. And this is where the term deepfake came from that subreddit. And at the same time, the original implementation of deepfake face swapping was made public to the world, so to speak. And so the creation of the subreddit at the end of 2017 is what really kicked off what we see as deepfakes today. In early 2018, the deepfake subreddit source code made its way to GitHub, and now a variety of people are working on that source code. FaceSwap is one well-known project in that regard. And FakeApp was a GUI application that was created in early 2018 that made it easy for kind of sort of anybody to create deepfakes. And so we began to see a bunch of creation and experimentation with deepfakes from early 2018 and on. So a little more than a year ago. In April 2018, Jordan Peele, a comedian, created a deepfake of Obama saying some things that he didn't actually say. And this video was really well done. It used his voice acting to solve the audio problem in that case. And the video, along with other people's kind of thinking about this problem, raised the specter of how deepfakes might be abused or used in a negative way. Shortly after that, some research was released regarding how you might detect deepfakes. The best known example is the detection of deepfakes via eye blinking patterns, basically. I think that's one of the cases that kind of everybody has heard of. And then a variety of other techniques were released. And most recently, some work that was originally released by Baidu called Deep Voice has matured a bit. And so now we're beginning to see synthesized audio, and we're seeing that combined with deepfaking in video. So There was a recent video released of Mark Zuckerberg also saying some things that he didn't actually say. But in that case, both the video and the audio were faked. And so it marked a new public example of sort of things to come. From a definition standpoint, oops, sorry, let's see here. And so from my perspective, the term deepfake seems to be, it's being overloaded quite a bit at this point. So in the news, I've noticed that essentially any video that's been doctored is now being called a deepfake by at least some folks in the media. So there seems to be a bit of confusion of what exactly a deepfake is. I personally think of it according to its original definition, which is a video in which the face for one person has been swapped onto the face of another person. There are now variations on this theme, so you have techniques aside from face swapping, such as puppet mastering, where you're controlling the facial movements of a person in a video, or lip syncing, where you're controlling the mouth in a video, for example. And for the purposes of this presentation, when we first put the videos together for my portion of the presentation, folks that I all worked with said, "Hey, where's the audio?" And I said, "Oh, I think you have no idea how hard it is to deal with both the video and the audio piece at the same time." So the scope for this presentation really ended up being limited to video. I coped with the audio piece for my part of the video creation stuff by just using fake closed caption as a replacement for the audio. So in our opinion, why we think deepfakes are or more likely will become a problem, online content today is frequently used for scams and other types of crime, and it's also been used to influence elections. So if you think about text and images, the way that these things are put together and used by folks, there are those types of media are already being used to do bad things. Hasn't really been possible to fake people in videos before, so deepfakes are kind of like a Photoshop for people in videos. Before Photoshop, it was maybe hard to edit an image, and people probably trusted images more. After Photoshop, folks don't really trust images that much. Now we're in that situation with video where it's becoming easy and low cost for anybody to create a deepfake containing a faked person doing something potentially bad. And so this scenario that's often described of a deepfake being created and dropped the night of an election, frankly, is pretty possible at this point, right? You can just take the software, it's freely available, you can stand up an instance in Amazon, you can pull your source video from an online content provider, train up your models, distribute it however you'd like. I think anybody could do that at any time if they wanted to. So the idea of the asymmetry of the cost of the impact is quite high. It would be easy to launch that attack, it would be lower cost, and the impact could be quite high, depending on what you were trying to accomplish. In terms of public examples, there are on the order of thousands of publicly known deepfakes. These are videos just floating around. I would say maybe the majority of those are related to adult content. For our purposes, we were mostly interested in the non-adult content stuff. And so we prepared a collection of 300 deepfakes that are used in Matt's portion of the presentation. Of all the known public deepfakes that we've heard of or have in our possession, none of them have been used yet for a malicious purpose per se. So there are great examples like the Jordan Peele video, and there are other examples that feature politicians, but everything has been to date sort of a proof of concept video. There was a recent video released of Nancy Pelosi that was mentioned in the press as being a deepfake by some folks, although it was not a deepfake. It was just a video clip that had been slowed down using regular video editing techniques. So there's really nothing special about the technique that was used there, although I do think the intent behind that video was actually a little malicious. And so it's an interesting case of using video for quote unquote offensive purposes, although it wasn't a deepfake. And probably one of the coolest recent developments from my standpoint as somebody interested in researching this topic. Symantec did release a report where they claim that they've become aware of 3 instances of criminals using fake audio to scam, as I understand it, CFOs out of millions of dollars at, I believe, 3 major corporations. And so I don't personally have all of the details, and I don't know that that's 100% true, but I assume that it is. And this then would be the first case seen where tech in the deepfake sort of realm has been used to actually commit a crime and has been verified and made public. So it marks a landmark for things to come, so to speak. So I'll quickly show a couple of examples here. The first example is just, I'll show 5 or 10 seconds of the Barack Obama clip that was created by Jordan Peele. This is a real clip, and the mouth in the video is controlled by the video creator, and there is audio where Jordan Peele as a voice actor recreated Obama's voice. So it looks very realistic, the audio is very realistic, and it would be a very convincing video to circulate. The second video is a video of the president of Argentina. I don't know if we have anybody from Argentina here, but with Hitler's face swapped onto Macri's face. So although the video wasn't released in an explicitly malicious sort of context, the idea that this video circulating, equating Macri to Hitler is certainly not a positive thing for him. And then we did, of course, have a Nancy Pelosi video, which is not a deepfake, but was released with malicious intent. So there are some examples out there that sort of straddle the line with respect to whether they're offensive or not. We haven't seen any major stuff yet. So in terms of research into the offensive use, I had originally set out to, my background originally was more in the vulnerability space, and I had in a past life done more reverse engineering of regular old software. And in looking at how deepfakes work, I wanted to do a little bit of reversing on how deepfakes are generated, face swap deepfakes are generated, and I wanted to go to sort of the lowest levels of the algorithm just to understand it in good detail. So I tried to take that type of approach to looking at how the face swapping algorithm works. So I'll go through a medium level technical explanation of how face swapping works, and then you can take the slides, which will be released later today, and dig into them if you want to get into more of that detail. Long story short, if you want to create a face swap deepfake, you have to go through about 4 steps. You have to essentially pick 2 people, person A and person B. At the end of the day, you're going to be able to face swap the face from person B onto the face from person A. So to keep things simple, I'm just going to describe this in terms of working primarily with videos. So you find a video that contains person A called video A. You find a video that contains person B called video B. You provide both of these videos to an extraction step, which pulls all of the data out of the videos that's needed to train up the face swapping algorithm. Then you actually train up the face swapping algorithm. You move on to your conversion step in step 4. And in this case, what you'll do is you'll find a net new video that's different from A or B, but it contains the same person as in video A. And then what you'll do is you'll convert video C into a deepfake by face swapping the face from video B into onto person A in video C. And then out comes the deepfake. So I'll go through it in a little bit more detail, but that's the basic process. From an extraction standpoint, I found all these details really interesting. I don't come from a video processing or computer vision background really, so it was cool to learn about some of these things. You take both video A and video B and you run them through the same extraction process. You extract each frame from the videos. You perform face detection, so this is the use of deep learning algorithm to detect the presence of a face in each frame of the video. In the case of the face swap implementation on GitHub, the MTCNN face detection algorithm is used. And so this identifies the location of the face within the frame. A lot of times, faces that are contained within video frames are not perfectly aligned. They're not aligned horizontally, they may be rotated. And for the training process, you want to have those faces aligned. So an affine transform or a rotation essentially of the faces is performed to take the unaligned faces to aligned faces. And I'll show you something visual now around that. So imagine that you have a video of this handsome guy, and imagine that you split that video into a series of frames. So let's say we have a video with 3 frames in it. We perform face detection on each of those frames, and you end up with something like this, the bounding box around my face. Now, some of the frames might have an unaligned face. That would be the case where the face is rotated like you see here. And so we would perform our transform and align all of those faces so that they're all level. Let's say that that was for video A. For video B, you have this other handsome guy here, and so we go through the same process for video B, extract the frames, perform face detection, align the faces, and at the end of the extraction phase, we end up with 2 sets of extracted face images, set A, set B, which is just a bunch of basically, my faces and a bunch of Matt's faces, let's say. So once we have our data set of faces there, then we move to the training stage. So this is where things get kind of interesting. There are now a variety of face swapping algorithms that are out there. The face swap repo on GitHub includes maybe 10 of them, I want to say. Although the original face swap algorithm that was released as part of the Deepfake subreddit remains the default option in that tool. And so I'll be describing that original algorithm here. There are others that you can take a look at if you want to go through the source. So the original face swapping algorithm uses a deep learning algorithm known as an autoencoder. For an autoencoder, essentially what you have are 2 independent models, an encoder and a decoder. You have some input data, such as an image in this case, so the image of the face. You supply the image to the encoder, and the encoder outputs essentially a compressed representation of its input, known as a latent image. So the encoder takes an image in, it spits out a reduced version of the original image. That reduced version is then supplied to a decoder, and the decoder then attempts to recreate the original image. Now, the training process runs for a long time, and this model attempts to learn all of the things that it needs to learn in order to recreate a copy of the original image with the greatest quality possible, so to speak. The reason that this process is, the benefit of using this approach basically is that the idea is that the autoencoder learns the important details of the images that are provided as input and discards the unimportant details, which is essentially how the model learns the characteristics of the individual faces. So with some images in place, then this is kind of what that looks like. Now, the thing that the face swapping algorithm does a little differently is it uses one encoder, the same as a traditional autoencoder, but it uses two separate decoders, one for video A and one for video B. And so the decoders are able to learn the facial features of the different people, so to speak, by splitting the decoding process. So we essentially provide all of our extracted faces to the encoder, which produce different latent images for person A and person B, which are then supplied to their respective decoders. And the model's trained up in this way. So if we overlay some images onto that, then this is kind of what it looks like from a visual standpoint. A picture of me, a picture of Matt goes into the encoder. Latent images come out. It's not what the latent images actually look like. It's just a representation. They're supplied to their decoders. The recreated images come out the other end of the decoder. They're typically lossy. It's kind of the nature of the thing. And this process is repeated until the quality of the output becomes high. If we further deep delve into the training algorithm, and I'll kind of stop going through all of the steps at this point, then we see that there's a little bit more complexity in reality to how this works than the simplified description in the last slide. The individual frames are actually pre-processed a bit by a training data generator algorithm in the face swap implementation. Then warped images are passed to the encoder. They run through the same process, and they're compared to target images generated by the training data generator towards the end of this process. And one thing that's pretty cool about Keras, which is an AI framework that you can use to build models like the one that's used here, is that you can export the models once they're constructed to PNG format, so you can kind of visualize what they look like. So this is just a PNG graphic of the top level model, which just shows the input layer, which would be a 64 by 64 RGB extracted face that would be fed into the encoder model, and then the output from the encoder model is fed into the decoder model. And this is what the encoder's network architecture looks like. So I won't go into all the details, right? But you can just see that there are a substantial number of different layers here and transformations that occur. And then you see the same thing from the decoding side of the equation. So the only thing that's kind of noticeable here is that you'll see on the left-hand side of the encoder, your inputs are this 64 by 64 pixel image, and your outputs of the decoder are also this recreated image, right, 64 by 64. So once we move past the training step, we get into conversion. And so this is where we want to take a net new video containing person A, and we want to create the actual deepfake, right? So we take our video C, which is our new video, we extract all the frames, we use MTCNN again to detect the faces, we go through that same exercise of extracting faces and aligning them. But the thing that we do here that's a little bit different is these are faces from person A, which we supply to our encoder, and then we supply to the decoder for person B. So instead of encoding and decoding via decoder A, we decode via decoder B. And so this is the step in the process that actually causes the characteristics of person B to be transformed onto the face of person A, or essentially where the faces are actually deepfaked, right, or where they're face swapped. So now this image containing the face swap person is output. It's aligned back to its original position in the video frame, and then all those frames are merged back together into a net new video, which is the deepfake. So this is essentially how the conversion process works. So with pictures, it looks kind of like this, or something like this. You'll see that the face swapping on the upper left occurs. The faces are rotated back to their original position in the frame. They're moved back into the frame. All the frames are then compressed into some video. So this part where the presentation gets a little interesting, and I'm almost done with my part. So what I wanted to do from an offensive standpoint was to experiment with creating the type of quote-unquote payload that I'd want to distribute in the context of an influence operation, politically. And so Representative Adam Schiff, who has an important role in the House of Representatives, as I understand it, and who has been pretty vocal about the deepfake topic and raising awareness with respect to this topic, stood out to me as a person that I might want to include into my video, A, because of his interest in the topic, and B, because we have a little bit of similar facial geometry, so our mouths are kind of the same. Well, those lips are a little poutier than mine, but hey. So what I wanted to do as I was learning about these different things was to create a video in which I have an original video of Adam Schiff, but I essentially control the mouth or replace the mouth in that video with my own, which in theory allows me to have a video of Adam Schiff saying things that he didn't actually say, kind of like the Obama video. I will say that the Jordan Peele outcome was a little higher quality than mine, but I'm sure that I'll get there soon. So the way this process works is I created a deepfake in which I face swapped Adam Schiff's face onto mine. So in the third image from the left, this is a small capture of what that deepfake looks like. It's kind of horrific if you if you look at it. And then what I did is I performed mouth extraction on that deepfake, and then I pulled each mouth out of the deepfake and overlaid it onto an original video of Adam Schiff. The overlay process is a huge PDAB, and so that was actually the hardest part of this process and an area where I need to continue to improve. But at the end of the day, this is a way in which you can take a video of somebody and quote unquote take control of their mouth, have them try and say things that you want them to say. So a comment on how this was created. Originally, I was thinking that I might try and re-implement the deepfaking algorithms myself. I realized that it wasn't really a sustainable approach in the sense that there's much more investment going into tools like FaceSwap than I would be able to put into mine. So I did use FaceSwap to create the deepfake, and then the DeepStar tool was used to perform all the other operations required to create the videos that I'll show you in a second. Really what I was interested in doing was creating kind of an automated kit that would allow me to create video fake news that incorporates mouse swap deepfakes that I could then automatically deliver to a list of email targets and SMS targets, so to speak, with the idea being that if I were on the eve of an election, I might pop in 10,000 emails or 10,000 phone numbers, click a button and change the outcome of an election, right? This is where I was at mentally. DeepStar supports all the operations that are required for that. So it allows me to automate the process of pulling down video from the internet, of extracting frames and whatnot from the video that I can use to train up the FaceSwap model. I'm also able to automate the process of pulling down stock footage, editing all of the clips together, merging in the deepfake. And then I also did a modest implementation of the mouth swap effect myself. And then the last capability with respect to offense in the tool is the ability to automatically deploy the video back out to the internet, to a video hosting provider, and then to populate a template and ship that off via email and text message to people. So kind of end-to-end script to influence an election or something like that. So this is the first video. I put a lot of time into this. I really wish that it would have come out a little bit better, but I still think that I did an okay job. So I'm sure you'll see a better version of this from me soon. So this is, again, there's no audio. This is a video of Adam Schiff with my mouth extracted from the deepfake and overlaid onto the video. So no big deal. So then if we move on to the next clip, this is a video clip that I produced in which that same Adam Schiff video is edited into a fake Fox News segment. And in the segment, Representative Adam Schiff declares his love of puppies. So I was nervous that if I showed the hard-hitting stuff first, that I would take the wind out of my sails. So I also created a video, which is a CNN version of the same clip, essentially. And then I created another version for MSNBC. And you can imagine that this would be possible to do for kind of any news network. I was hoping that I'd have time to get to, for example, leading news networks in Russia, China, North Korea, and all that stuff. I just didn't have the time for it. And so after having created the videos then through the use of the tool, I was able to automate the delivery of a link to the videos out via email, and then to perform the same operation out via SMS. So SMS seemed interesting to me because I don't think that it's a vector folks would really think about as obviously as they would think about email or something like that. So kind of coming to a conclusion then, the last piece of video that I did create, which is a little bit more edgy than the puppies video, is the same format, but a clip in which Representative Schiff completely exonerates Donald Trump. Clearly this didn't happen. I did send this video to my mom, who is a left-leaning person that lives in Northern California, and she was upset for a few seconds and then figured it out, so it was rewarding for me. Beyond that, though, did not distribute the video. So originally I was planning to do that. Part of the talk description implied that I would do that. at the time that we proposed this talk, it seemed like a good idea. As things became more real, it seemed like it was a little bit riskier. So we'll do that maybe in the future. So at the end of the day, from the offensive side of the equation then, I think essentially what I tried to do here was to take the sort of thing that everybody had been thinking and make it real, which is, hey, if you have an Obama video, great, but like, what would somebody do to actually distribute that thing? You might package it up into fake news, you might automate the delivery process. And so making that all kind of kiddable and easy to do is what I worked on. And then for these videos, I wanted to show some real examples of what you could expect to see. This is not very hard to do. It's maybe like 2 or 3 weeks worth of work. So the barrier to entry is low. And I think the point for me at the end of the day is like, if somebody did a slightly better job of creating these videos and deployed them on an eve of an election, would we collectively be equipped to deal with that? I don't believe the answer is yes. I think that somebody could actually do this and somebody may very well do it. So something to keep in mind. With that said, I'll turn it over to Matt, who will share everything about the solution side of the house.
Awesome. So now that Mike's kind of covered how we can create deepfakes and how we can use them offensively, let's switch gears a little bit and talk about actually detecting deepfakes. So one of the first points I want to make is that humans are horrible detection machines when it comes to image manipulation. And a study done by some European researchers on 143 computer science students, what they did is they gave them a series of 60 images. And within those images, 50% of them were pristine images, real images, so they hadn't been manipulated. And half of those images had been manipulated using 3 different types of deepfaking methods. So what those researchers ended up found is that at best, humans can identify real images with a rate of about 80%, which is fairly poor in my opinion. But then when we start talking about images that had been actually manipulated, what we're actually going to find in deepfake videos, at best, humans are able to identify those forgeries at a rate of about 75%, and at worst, a rate of 40%. So we can't rely on humans to detect deepfakes, unfortunately. So that army of human analysts that you're going to deploy to detect deepfakes is not going to work. Luckily, there are a number of methodologies that we can use to detect deepfakes. And a bunch of these methodologies had actually already existed in the image forensic realm. So one of those ways is looking at the signal level. And what we're talking about here are properties that are inherent to the image itself. So for example, if the image had been compressed using double JPEG compression, for example, that's usually a red flag that that image has been manipulated in some ways. Same things if we go and say find like artifacts left behind by a GAN when you're creating a deepfake video using an audio coder. Those are things that we can detect at the signal level. At the physical level, we're talking about things like lighting conditions, shadows, reflections, and so on. So an example of this would be if a light source on a face in a video is coming from the right, but all the other objects within that video indicate that the light source is coming from the left, that's a huge red flag that we're probably looking at a deepfake. At the semantic level, we're talking about really consistency of metadata. So if a video gets released and it has a public figure in it, and they say that this public figure was at this location at this time and day, we can actually go back and verify that that public figure was indeed at that location on that date. So these 3 methods that I just talked to, signal, physical, and semantic level, these are things that methods that have been used in traditional image forensics. Something that's new to detecting deepfakes is using physiological signals. So these are things like essentially involuntary traits that we all have as humans. So things like breathing, eye blinking, facial orientation, and so on. What's unique about using physiological signals is that these methods can be tailored to an individual or they can be generalized, so they work for any number of individuals. 2 things that they at least weren't mentioned, but aren't really detection methods per se, are video authentication. For example, blockchain gets thrown around a lot right now, or white or blacklisting. So while these aren't detection methods per se, they could help in the short term with preventing deepfakes from causing a bigger problem while we catch up on the detection side. So now that we've gone over some of the methodologies that we can use to detect deepfakes, let's actually talk about some of the actual implementations that have been published. So for this section, I'm going to assume you at least have a basic understanding of computer vision techniques as well as neural networks. Because I'm going to have to talk to some of this stuff at a high level, but I will have to get into some of the details. The other thing I want to note is that published research on detecting deepfakes didn't start coming out until the summer of 2018. So this is very much a new and ongoing area of research today. So one of the methods you've probably heard about, because this made its round in the news because it was one of the first ways of detecting deepfakes, is by measuring how many times someone blinks in a video. So the reason that eye blinking works is that this is obviously a physiological trait. All humans do it, and it's involuntary at a certain frequency. So these researchers recognized that, and they also noticed that within deepfake videos, the target was not blinking. So what they did is they trained a neural network image classifier to simply detect whether an individual's eyes were open or closed. They then ran this over a series of video frames, and based on the number of positive detections they had for the target's eyes being closed, he could then determine whether or not the video was a deepfake or not. This was a great method for about 2 weeks until one of the offensive researchers figured out that the issue that would correct this was to include more images of your source with their eyes closed in your training data set for the deepfake algorithm. So unfortunately, this is no longer a viable method of detecting deepfakes. A signal-based level is using the photoresponse non-uniformity pattern, the PRNU pattern. The PRNU pattern is very interesting in that it is a digital fingerprint for a camera because it's based on factory defects on the light sensors for cameras. So this is actually a technique that was originally used for traditional image forensics that has since been kind of ported over to be used for detecting deepfakes. In this case, what these researchers did is they extracted a bunch of faces out of a series of video frames and then split those into 8 uniform groups. For each of those 8 uniform groups, they then calculated the average PNU pattern and then took the mean normalized cross correlation score between each of those 8 groups. And those are the results that you actually see plotted here on the right-hand part of the slide. So as you can see, for real videos, there's a very good chance that there's going to be a high correlation in the PRNU patterns across those groups, which you would expect, because most likely that video has been taken with the same camera. For deepfakes, on the other hand, since we are using images from other sources, other cameras, that PRNU pattern does get disrupted, and you can indeed see that is the case. So the one problem or downside, to say, with using the PRNU pattern is that oftentimes videos are shot from multiple cameras and from multiple angles. So this method will throw a lot of false positives if you do run across videos of that sort. Some of the other methods to detecting deepfakes involve inventing novel neural network architectures. One of the more interesting ones is called MesoNet. The basic premise behind MesoNet is that at a microscopic approach, which is the level that most of these complex convolutional neural networks operate at, you lose too much information. So because of that, you're unable to really determine whether or not a video is a deepfake. At the same time, at a high level, at the macroscopic level, which is the level that humans operate at, we have issues detecting forgeries. There's really too much information. You don't know really what to focus on to detect whether or not something is a deepfake. So the hypothesis that these researchers had was that if we operate at an intermediate level, at the mesoscopic level, then we should develop a model that has the best chance of detecting deepfakes. The way that the authors ended up building out this model was to start with a very complex convolutional neural network and bit by bit remove layers. As they continued to remove layers, they would again retrain that algorithm and see how well its predictability was. If there was no loss in predictability, they continued doing that. What they ended up with was a convolutional neural network that had 4 convolutional layers and then 2 dense layers on top of it. One of the things that's at least worth mentioning, but I'm not going to go into too much detail on, is that some researchers have also implemented a capsule network. So a capsule network were an old idea first proposed like in the early 2010s, but were later kind of put to the side in favor of convolutional neural networks. So in this case, these researchers actually brought back these capsule networks and have used it to successfully detect deepfakes. So recurrent neural networks in particular are actually well suited to detecting deepfakes. And the main reason for that is that with recurrent neural networks, we can actually capture temporal information that we can't capture with convolutional neural networks. So in this case, what we're really looking to do with recurrent neural network is to exploit the fact that these deepfake videos contain temporal inconsistencies. Especially if you look at deepfakes frame by frame, there's notable issues when you go frame by frame. For example, the face won't be the same frame by frame, lighting conditions may change, or shadows may be off. A convolutional neural network isn't going to catch that, but theoretically RNN should. So this really, why does this work? As Mike kind of explained, the autoencoder works frame by frame. And what this means is that it has no sense of temporal awareness, so it's not aware of previous faces that it has generated. So because it's unaware of these previous faces that it's generated, there is no connection between those faces as you look by frame, and that's really what we're hoping that these recurrent neural networks pick up on. This idea, rather than just feeding frames into the recurrent neural network, another way this has been extended is by using traditional image forgery detection tools and then taking the outputs of those and feeding that stream of information into the RNN and hoping that the RNN learns that there's that temporal forensic information contains inconsistencies and can then detect whether or not a video is a deepfake. One of the more, at least in my opinion, like clever methods for detecting deepfakes involves looking at the orientation of your face. So what these researchers noticed was that when you do the face replacement for a deepfake, you tend to disrupt the orientation that someone's face has because those central facial landmarks no longer really line up with the rest of the face. So what they did is they estimated your facial orientation by using just your central face landmarks. So that's your eyes, your nose, and your mouth. They then, using all the information from your face, so then including your forehead, your cheekbones, and your chin, again, take another estimate of your facial orientation. If both of those estimates are fairly similar to each other, then it's more than likely that video is real. If those estimates are significantly off, then more than likely we're looking at a deepfake. So two more additional kind of signal-based methods involve looking for artifacts left behind by the autoencoder as part of the deepfake generation process. So one type of artifact that's left behind are the face warping artifacts. So as Mike kind of talked about, as you map that face from the source onto the target, you're going to have to scale the face. You're going to have to rotate it usually. There may be some shearing, cropping, and so on involved. And all these things are called affine transformations. So when you go through these affine transformations, we should be able to find pixel level information that indeed those transformations were done on this image. Another way that we can also detect deepfakes is by looking at what's actually happening internally within the GAN as part of creating a deepfake. Within the GAN, the actual weights are constrained, and this is to help prevent pixel values from blowing up. However, because that GAN is constrained, what that results is that you have a limited frequency of pixel values that can be generated from the GAN. And while this may look okay to us as humans, at a pixel level, it doesn't make a lot of sense because you don't expect to see, for example, like uniform distribution of pixel values within an image. That doesn't make a lot of sense. So by measuring these pixel frequencies and pixel saturations, we're able to get an idea of whether or not the video is a deepfake. And the whole reason that these methods still work while the deepfake looks legitimate is that looking correct is not the same thing as being pixel-wise correct. So there's a lot of information on this slide, but there's two things that I really want to mention here. One is that these detection methods that I've gone through, the vast majority of them are fairly accurate when you have access to the raw video. So we're talking about video that has not been compressed. However, in reality, more than likely, you're going to be dealing with compressed videos. In order to ship videos around on the internet, by default, sites like YouTube or Venmo or Facebook have to compress that video. And there's varying levels of compression that we can talk about. There's high quality video compression and low quality video compression. But one of the key takeaways I want you to take away from this is that as the video quality degrades, the predictive ability of our models to actually determine if a video is a deepfake also degrades. All the methods that I've talked to so far are generalized detection methods. But we can also tailor detection methods to work for an individual, for example, like high-profile public figures. So this is one of those methods. So in this, researchers noticed that everybody has distinct facial and head movements. And when you create that deepfake, as part of that creation process, you interrupt those unique head movements. So what they did is they extracted 10-second clips from a video, and that ended up creating a feature vector containing 190 individual features. They then used a sliding window approach of 5 seconds, and then gathered up a number of these feature vectors and fed those into a support vector machine. The graphic that you can actually see on the right is those feature vectors mapped into two-dimensional space. What I really want to draw your attention to are those gray dots kind of on the bottom right part of that graphic. Those gray dots represent President Obama, the real President Obama. If you look at those black dots that are clustering kind of to the right of those gray dots, that is actually a deepfake of President Obama. So you can see that there is some kind of method to this madness where you can actually tell that those unique facial features that indicate your head pose are actually uniquely identifying individuals, and they do get disrupted when you create a deepfake of that individual. Another thing that's really nice about this method is that you only require real videos of an individual in order to train it, unlike all the other methods where you have to go out and actually collect deepfakes or create them. With that said, there's still a number of open detection issues that have not been resolved yet. I already talked to kind of the video compression resolution one, but as that video quality degrades, so does the predictability of all of these models. Another just issue is there's been a lot of improvement in deepfake generation capabilities. So it's a lot of these detection capabilities are still playing catch up. Another issue, and Mike somewhat talked to this, but there's 3 different ways to create deepfakes. Through the use of puppeteering, lip syncing, or more commonly what you see, face swapping. None of these models are able to successfully detect all 3 types of deepfakes. So this is still an outstanding issue. Another issue, and I call this selective deepfaking, could be one of 2 things. One is where only small parts of the video have been deepfaked. So if you have a 5-minute video, maybe only 30 seconds of it have been deepfaked. Another issue is where you have multiple people in a video, where only one individual or maybe a couple individuals have been deepfaked, and everybody else still looks real. So we've actually been looking into deepfakes now for a while. One of the things I wanted to share was some of the research that we've done into developing a single model that actually can detect all 3 types of deepfakes. So I actually call this model MouthNet, and you'll find out why here in a little bit. But it's an image classification algorithm. The model is very basic. For the backbone, it's using the latest version of the Exception ResNet model, and then we have added 2 additional dense layers on top of that. So the reason I call this MouthNet is because unlike all the previous detection methods and what's been published is everyone's looking at the entire face. For this model, we only look at the mouth. So what we do is we crop out square sections of with the mouth in the center of those and feed those as input into our model. So the reason I expect this to catch all 3 types of deepfakes is that by definition, all 3 types of these deepfaking methods have to alter the mouth. Kind of the lowest common denominator in terms of what gets altered within the video is the mouth. Like you may not touch the eyes, you may not touch the nose, but you have to touch the mouth at the end of the day for it to be a deepfake. One thing I want to note is that we did somewhat limit our data set. We didn't grab anything from the deep web. We kept everything pretty much safe for work because this is a data set that we are going to be releasing later. The other thing I want to note is that we had about 200 videos that we used for training, and then we held aside videos for both our validation and test sets. So when I report these numbers, just keep in mind that these are videos that the model has not seen. Another thing I want to note is that I do have examples of all 3 types of deepfaking methods within this data set, which is also unique. While face swapping methods are largely are more represented within this data set, we do have lip syncing and puppeteering methods within it. And the other thing is that I did not make any kind of distinction between video quality. So we have both high quality videos and low quality videos within this data set. So to give you a little bit more intuition as to why this model should work, these are 2 pairs of images that I pulled out from the same video. So this is holding video quality constant. You can probably already visibly notice that the deepfaked mouths look substantially different than the real mouths. So this is one thing that I was hoping the model was going to learn. The other thing that I was hoping the model was going to learn is that mouths have to go through that AFIN transformation process in order to be successfully mapped from the source of the target. So I was hoping that the model would also learn to pick up these transformation artifacts that are left behind, especially around the mouth region. So these are the results. In terms of the actual image classification problem, our validation accuracy was 83%. However, we did implement MesoNet, which is what I use as our baseline model for all of our data sets, and its validation accuracy was 72%. Granted, I used the faces for MesoNet, not the mouths. So I do believe that by using the MAUs, that actually does help to, one, simplify the amount of information that the model has to learn and the features that it needs to know in order to make its detection. And the other thing is that I think it's far easier for the model to segment real MAUs and fake MAUs rather than trying to figure out, hey, there's 3 different types of deepfaking methods, and I need to actually learn that these 3 types of faces could be fake. One of the other issues I'll point out is that actually both of these models were overfitting on this data set, and I think that's for mainly the reason that I did not have enough puppeteering or lip syncing videos available. Just simply put, like face swap there's tons of those videos that you can easily get online, but there's a lot less that you can easily grab for puppeteering and lip syncing examples. So I think that if I were to go and grab some more of those examples, that'd help address a lot of this overfitting problem that you're seeing. So in terms of the test videos, the 100 test videos that we held aside for our test set, I used a very simple detection method. We would just extract the first 100 frames that we could find with faces. We then averaged the predictions of the models, and if that was greater than some threshold, then we considered that video to be a deepfake. So in this case, the threshold that I preferred for this model was 0.9. So using that threshold, we found we were able to successfully detect 41% of the deepfakes, but we did misclassify 10% of the real videos. One of the other things that I looked into was the impact of image size. So there's been increasing evidence that image size does matter when you feed it into a convolutional neural network, and they aren't necessarily scale invariant. And that's kind of why we have these ideas such as like progressive resizing emerging. So what I did here, in order to see if the image size actually did impact the model, is I broke these images into 4 different buckets of various pixel sizes. I then trained 4 of the MouthNet models on each of these bucket sizes, and then again ran it through the same test. In this case, I used a threshold of 0.5, and we caught 53% of the deepfakes. However, we did misclassify 26% of the real videos. So we did end up detecting more of the deepfakes, but at the expense of also throwing more false positives. One of the things I also want to point out is I did plot out the matter model accuracies as a function of the score threshold that we used. You can see that our baseline model is still far below the MouthNet models. So given how difficult this data set is, I'm actually fairly happy with the results that we got from this model. And I do believe that it would be a viable model moving forward for detecting deepfakes. Another thing that I did is I went through and looked at all the videos that these models were missing on. And these are some of the kind of trends that I saw. One is just low resolution videos, and our review has spoken to this, but low resolution videos are causing serious problems for all of these models. So one of the things I've started doing moving forward is that not only do I grab the highest quality video that I can get, but also grab the lowest quality too. I'm hoping that by augmenting my data set in that way, that'll help improve some of the accuracy there. Another interesting source, because we had a number of misses here, were movie trailers and baby videos. Movie trailers, I actually suspect that these are digitally altered, and the model is actually picking up on that and therefore misclassifying movie trailers as deepfakes. Baby videos, on the other hand, I think this is mainly just a training set issue, but it's so some of the issues that you can expect to see in the wild. I only included 1 baby video in the training set, but there were a number of instances on the deepfake side where baby faces had been deepfaked onto adults' faces. So I think what the model learned is that if it saw a baby face, most likely that was a deepfake, and those are the sources of some of those misclassifications as well. I've also spoken to this, but with selective deepfaking, multiple people within a deepfake causes a lot of problems, especially when some of those are real faces. I think the easiest solution to this is actually to cluster faces based on similarity, and then run your predictions over these clustered set of faces. Another major issue, and this is the same for all these deepfake algorithms, is the facial extraction model that you're using matters a lot. We were using MTCNN, which is, it's not a bad model, but it's definitely not state of the art at this point. So we ended up picking up quite a bit of noise. In some cases, like logos are always being detected as faces, and there's other instances too where we need to make sure that we eliminate background faces. So I think by eliminating some of these sources of noise will help to improve the accuracy of these detection models. So to wrap up, what I want to do is just briefly introduce DeepStar, which is the detection tool that Mike and I have been working on. So really build DeepStar because it is a huge pain to try to build a deepfake data set. There's no tooling that's really available, and you have to go out and gather the videos, extract frames, and then even after you extract the frames, you kind of need to figure out what you want to look at, phases, mouse, and so on. So this can be really helpful for building out these data sets. We've also added some additional capabilities that can help you test your detection algorithms as well. Another thing that we're doing is we're also releasing the source code of both the models that I've talked to, MesoNet and MouthNet. So you can find the training code in this open source repo as well. You can go and start training your own algorithms or your own detectors. So the source code, it'll be available under the ZeroFox open source organization under the name DeepStar. And this will be available probably by the end of this week. So with that, we're almost out of time, but I do want to remind you that you can come up to the speaker wrap-up room afterwards and ask us questions. So thank you very much.